Adorable story alert! So I was hanging out with my 2-year-old second cousin in the ocean in Florida, and we're jumping up and down with the waves, and it's fun, but then the water got all calm, and I said, oh, no more waves, because, that's the top tier of communication I'm going for with a 2-year-old. But then he said, don't worry, there'll be more. And I was like, how do you know? And he was like, it's a cycle. Yes, it is a cycle. The Earth is filled with cycles. And if my 2-year-old second cousin knows it, you should know it too. The universe is the great recycler. All the stuff that we've got on Earth, every last particle of matter or calorie of energy has been around since the Big Bang. It just keeps getting repurposed over and over again. And when it comes to matter, at least, Earth is essentially a closed system. All matter gets passed around in continuous biogeochemical cycles, which are pathways for molecules like water or elements like carbon and nitrogen and phosphorus to move through all of the Earth's various ecological and geological compartments. Now, of course, we couldn't possibly talk about how all matter gets cycled around Earth in one video, because the Earth is pretty big. But consider this an introduction to biogeochemical cycles starring my 2 personal favorites, carbon and water. Now, I'm sure you already know about at least one kind of planet-wide recycling because it's the most obvious to us, the hydrologic cycle, which describes how water moves on above and below the surface of the Earth, driven by energy supplied by the sun and the wind. And talking about the hydrologic cycle, it's most useful to think about all of the water on Earth being held in a series of reservoirs. The ocean, for instance, or the atmosphere in the form of clouds or in polar ice caps. So not only does water cycle through different places, it also takes different forms at different places in the cycle, liquid, solid, or gas. And since it's a cycle, there is no beginning and there is no end, so where we start our discussion is arbitrary, but we're going to start it off with precipitation. Rain, hail, snow, sleet, grauple, all that stuff is precipitation. It happens when water that's being held in the atmosphere condenses or turns from a gas into a liquid and then occasionally freezes into a solid right up in the air. The opposite of condensation, of course, is evaporation, the conversion of a liquid into a gas, and when a substance converts straight from a solid to a gas, that's sublimation, and when it's from a gas to a solid, that's deposition. And now you know. But back to condensation. It's responsible for the formation of clouds, which happens when air containing water vapor rises and cools or is compressed to the point that it can no longer be a gas. At this point, the vapor forms droplets. This is the same thing you see happening on your glass of iced tea on a humid day. The water in the air around the glass gets cold and turns from gas into liquid. So a cloud is just a big pile of condensed water droplets. In a sense, it's a gigantic floating reservoir. Clouds are a handy feature of the hydrologic cycle because as they drift over the landscape, they move water around the globe, so water that evaporates over the ocean can be deposited somewhere else. Otherwise, if water always got deposited right where it evaporated, the precipitation would be almost all right over the ocean, because that's where most of the evaporation on Earth takes place. So wind moves clouds, and as water keeps condensing, clouds get heavier and heavier until our old friend gravity takes over and pulls the condensed droplets to the ground in the form of rain, or in the form of snow, or hail, or sleet, or grauple. So now the water's on the ground, but gravity continues to work on it, pulling it toward its resting place, whatever that might be. It either pulls the water across the surface of the land toward the lowest point in a process called runoff, or it pulls it underground. Water can be trapped or stored for a little while in places like lakes and ponds and wetlands, but most of the water that falls as precipitation gets pulled lower and lower and lower as runoff through the creeks, streams, and rivers until it reaches the oceans. Now, in really cold places, water of course freezes and hangs around as ice in certain places for thousands of years at a time, like at the poles and glaciers and on mountaintops, but when it melts, most of it, too, runs off into the oceans. So you see where this is going. Oceans are a big deal. They're pretty much the biggest deal. They're the reason that we have the hydrologic cycle in the first place. They're also the reason we have awesome stuff like weather and life on Earth. The weird thing about oceans, though, is that they're salty. And there is a reason for this. As water runs to the ocean, it erodes minerals like salt from soil and carries it to the ocean. Now, water heading to the ocean might not taste salty, but the salt's in there. But here's the thing. When the water evaporates again, the salt doesn't evaporate with it. It gets left behind. You keep this up for a few billion years with pure water evaporating from the ocean and then returning with tiny amounts of salt, and that's your recipe for 1 billion cubic kilometers of brine. And all this shows that the world's oceans are literally the last stop for all the liquid water on Earth. The only way to get out of there is through evaporation, and that leaves all your minerals behind. Now, living things also have their role to play in the hydrologic cycle. In both plants and animals, the breakdown of carbohydrates to produce energy produces water as a waste product. So we lose water through evaporation from our skin. We also exhale water vapor, and of course we we pee it out. Indeed, most organisms on Earth are made mostly of water, although that water cycles in and out of us pretty quickly. In plants, water is sucked up through the roots and moves up to the leaves, the gas exchange organs, where it evaporates quickly. This process is called evapotranspiration, and since there are so many plants here on Earth, it's responsible for a good amount of the water that enters the atmosphere. This process is essentially the opposite of condensation in that it turns liquid water into gas. The energy of the sun drives evaporation, whether it's from the surface of the ocean or from treetops and leaves, and then once all that water evaporates into the atmosphere, we're right back where we started. It's a cycle! So now that you know a little bit about the hydrologic cycle, it's a little easier to understand how the carbon cycle works. Carbon is one of the most abundant elements in the universe, and here on Earth, it's always on the move, just like water jumping from one reservoir to the next. And that's a good thing, because A, all living things require carbon for their structure and to fuel their bodies, and B, it's a big component in a bunch of non-living things as well. It's in rocks, in the ocean, trapped in ice, plus it's in the atmosphere, where it helps regulate the temperature. Without carbon dioxide, Earth would basically be a frozen wasteland, so lucky for us, there's a whole pants load of carbon out there, because we need it. Let's start out with the carbon in living things. If you were to take all of the water out of your body, carbon would constitute about half of what remained in the little pile of dust that used to be you. And the first biological carbon reservoir is plants. They absorb a bunch of carbon dioxide out of the atmosphere because they need it to photosynthesize. But CO2 is also one of the byproducts of respiration, the process by which they use that energy. So plants take in carbon dioxide from the atmosphere during photosynthesis and then release CO2 back out into the atmosphere during their respiration process to make ATP for all their cellular functions. And right now, you're like, wait, no, isn't the deal that plants get to take in the carbon dioxide and animals get to breathe it out? Well, yes and no. It's just that plants take in more CO2 from the atmosphere than they give off through respiration. The rest is like their profit. It's what becomes the body of the plant. That's right, that big old massive tree, all of that mass came from gas. Pretty cool. So carbon absorbed by plants has three possible fates. It can be respired back into the atmosphere, it can be eaten by an animal, or it can be present when the plant dies. And if a tree falls in the right kind of forest and it's not allowed to decompose normally because a bunch of other plants all fell right on top of it and they die and get buried and squished together and form rocks like coal. We call these carbon-rich geological deposits fossil fuels. Lately, one of humanity's very favorite pastimes is digging up all of this old carbon in the form of coal and oil and natural gas and burning it to fuel our pretty much everything's. But I'll get to that later. Another extremely important carbon reservoir is the ocean. Now, carbon dioxide dissolves really easily in water, and once it's in there, a lot of it's used by phytoplankton, tiny plant-like organisms that form the base of the marine food chain. They use carbon in photosynthesis, and they also use it to make calcium carbonate shells. And when these guys die, their shells settle to the bottom of the ocean, pile up, become compressed, and over time, make rocks like limestone. Now, limestone obviously doesn't burn super well, so it's not considered a fossil fuel, but as limestone deposits are eroded by water, the calcium carbonate is broken down to eventually form, among other things, carbon dioxide and carbonic acid. We make lime and cement by heating limestone, which produces a pretty good amount of carbon dioxide. And when we do burn fossil fuels such as coal and petroleum products and natural gas, it also releases carbon in the form of carbon dioxide that's been stored for hundreds of millions of years in the geosphere, which is just a fancy sciencey word for Earth rocks. This process is what started the atmospheric carbon dioxide levels rising like crazy in the past couple hundred years, and the excess of carbon dioxide in the atmosphere causes global climate change because CO2 in the atmosphere prevents some of the sun's energy from re-radiating back out into space. So yeah, our planet is getting warmer because we've been burning through this massive reservoir of carbon that we had locked underground. This is causing all kinds of problems that we can see already, and it's very likely going to keep causing bigger and bigger problems with time. And the situation could be helped a lot if we would just stop unlocking all of that carbon and spitting it in the atmosphere, but in some respects we don't even have control of the situation anymore because of ice. Remember how I said that carbon is often trapped in ice? Well, in places like Siberia and northern Canada and Alaska, cold places that also have plants, they contain huge carbon reserves that are trapped in permafrost, ground that's frozen year-round. These places are basically frozen wetlands that add another layer of dead plant matter each year. But as permafrost melts, these dead plants decompose, and huge amounts of carbon dioxide and methane are released into the atmosphere, creating a positive feedback loop. Our carbon-burning lifestyles unleashing this other huge carbon reservoir which keep the whole greenhouse effect going with or without us. Just saying. Sorry to end on such a frightening and depressing note, but the stability of global climate is is not as stable as we would like it to be, and the fact that we're throwing it out of whack is one of the most important reasons to study ecology in the first place. This episode of Crash Course was written by myself, Jesselyn Shields, and Blake DiPastino. Our technical director is Nick Jenkins, who is also our editor and is also standing behind the camera right now. Graphics are courtesy of Amber Bushnell and Peter Winkler, and our sound designer is Michael Aranda. If you want to review any of what we went over in today's episode, check out the table of contents over there. And if you have any questions or comments or corrections or ideas for us, we're on Facebook and Twitter, and of course, down in the comments below.